Well, in addition to designing the work and trying to figure out how the work should be done by a specialist, generalist, and how can we make it more efficient, sometimes we need to simply measure the work. I mean, think about some of the previous lectures on facility layout. We needed some basic information, for example, in product layouts about how long it took to do a certain task. So work measurement, which is going to focus on measuring how long it takes to do an existing task, is something which can be very important. So a couple ways to do work measurement. The most obvious way perhaps is to actually go out and measure someone doing the job, and that's referred to as a time study. So if a job is existing, if someone is doing the job out on the factory floor, you can simply have an employee, industrial engineer, or more likely an intern, go out and watch the person doing the job multiple times and form an estimate of how long it takes to do that job based on the workers doing the job. Now, if it's a new job that hasn't been done before and you're trying to figure out how long you think it's going to take, well, then there are published time standards, or of course nowadays computer programs that include time standards, where you can enter in the elements of the job, what's involved, basically the same elements that we talked about in the previous video when talking about motion study. And then based upon those work elements, those third legs, you can get an estimate using the time standards of what the new job should take in terms of a time. Well, let's focus on time study here. So again, this is something that a lot of interns have done in the past. I read all the internship reports, and it's not an uncommon chore for an intern to do at least some of this over the summer. So what's involved is workers doing the task, and you just want to go out and watch someone doing that job, but you need to be concerned about whether or not that worker is a typical worker, okay, because workers differ in their performance levels, and you want to have an estimate of the time needed to do the job, which is not necessarily depend upon which worker is doing it. And of course, you also have to allocate time for things like fatigue. You know, it might take them longer to do the job later in the day, and other factors as well. So let's introduce some basic terminology here that we can use to help us calculate or get a good time estimate. OT, that's going to stand for the observed time. So that's what the intern actually observes when the intern goes down and watches the person doing the job over and over again. They're going to watch the person do the job multiple times, take an average of those times, and that average time is going to be called the observed time. Now this next item is a little tougher to get a handle on because it requires you to have some information about the different workers being observed. But ideally, we would have an estimate of the performance of the worker being observed relative to an average worker in the facility. I'm calling this the performance rating, or PR for short. So for example, if an average worker had a performance rating of 1, and the worker I was observing had I thought was 10% faster than that average worker, then the performance rating of that worker that I observed would be 1.1. They're basically working at 110% of normal, so they get a higher performance rating. If they were slower, 10% slower, then they get a performance rating of 0.9. So the normal time is a time to do the job, the average time to do the job by an average worker. So you're going to take that observed time that you watch the worker do the task on, and then you're going to multiply that by the performance rating to get the normal time. So basically, if the worker that you observed is faster than normal, the performance rating will be greater than 1, and so it's going to increase the normal time to be an amount greater than the observed time. And we'll work through an example of this in a little bit. Now, perhaps even more, a little more fuzzy is the allowance factor. Okay, and again, it sounds like a fuzzy concept, as we'll see here, but there are standards that we can apply. Allowance factor is the idea that the worker gets tired throughout the day. They have to take restroom breaks and so forth. Again, any sort of physical activity, there's going to be variability in the time required, and you want an average time which you can apply reasonably towards the end of the shift as well as at the beginning of the shift. So the allowance factor is going to be allocating an extra amount of time to the task for the worker to do things like take restroom breaks, get materials, and also for the fact that they are probably going to get more fatigued as the day progresses, and you want to make sure that they don't you don't estimate a time that's too low for the worker to do the job. Once you have the allowance factor, then to calculate the standard time, this time you're actually going to be using for planning purposes and assembly line balancing purposes, project planning purposes, and so forth. You simply take the normal time, which you had up here, and multiply it times the allowance factor, which we have here, and we get the standard time. And again, for the different types of work being performed, there are generally allowance factors that can be calculated, that are published based upon experimentation as what's reasonable. If someone's lifting heavy loads and so forth, you're probably going to have a greater allowance factor than if they're doing light assembly. So these numbers may seem a little fuzzy, but you can get reasonable estimates for these numbers. So here's a little example just so we understand how the math works. Suppose that an experienced worker is observed assembling a part 30 times. The average observed time is 3.5 minutes per unit. The worker is assumed to be about 20% faster than the average worker, and again I said assumed here, but this could be based upon past experience with the worker doing other types of jobs. And the firm has a policy of allocating an extra 10% of time for fatigue, restroom breaks, and so forth. Again, this can be based upon the nature of the work that's being done. So first we calculate the normal time, which is our observed time of 3.5 minutes, plus our performance rating. Worker's 20% faster. The performance rating is 1.2. So 3.5 times 1.2 gives me a normal time of 4.2 minutes per unit. And then I have to throw in the allowance factor of 1.1, basically an extra 10% of time, and to calculate the standard time. So I take the normal time they just have up here, 4.2 minutes, multiply it times my allowance factor of 1 plus 0.10, and that gives me a standard time of 4.62 minutes. And there's actually a couple different ways to figure out an allowance factor depending upon the nature of what's being allowed for. The text talks a little bit about that. This is the simpler approach where you just add the extra percentage to 1 to get the allowance factor. And this example then, I have a standard time that turns out to be 4.62 minutes. And that's the time that I would use for planning purposes. Now, in that example, I just said that we needed 30 observations, but if I took my 30 observations and calculated my average, if my standard deviation was really, really high, I might not have a lot of confidence in that average. So it might be worthwhile to go through this calculation here to see if I've really got a sufficient number of observations required to give me my desired accuracy. So after my initial 30 observations, I can, based upon the standard deviation of those observed times, as well as the mean observed time I got from those 30 observations, I can plug them into this formula down here and try and see, well, gee, is that the sufficient number of observations, or do I need to collect many more observations? So if I'm trying to find n, the number of necessary observations, and my desired percentage of accuracy is a fraction I'm going to call a here, and the confidence I want to have in that estimate is, say, 95.5%, which corresponds to a z-score of 2, and we'll talk more about z-scores later. Don't really want to do it at this point in the course. You've all had a statistics course, but I'll go into more of a review of z-scores when I talk about quality management later in the course, but for now we'll just accept it as magic. If I want a 95.5% confidence level in the estimate, that implies a z-score of 2. That's going to appear here in this formula. Well, then I can apply this formula to be 95.5% confident of being within a% of the true mean time, set n such that n equals z, or 2, times my standard deviation divided by a times my observed time, and then square that whole thing, and that's the minimum number of observations I need. So let's take a look at my example that I had earlier. I want to be 95.5% sure that my new standard time for this part that I'm making, the circuit board that I'm putting together, is no more than 2% off the true mean. If the observed time was 3.5 minutes, and the standard deviation of 30 observations was 0.3, then I plug the standard deviation in here. Here's the percent off I want to be from the true mean. Well, that 2% corresponds to 0.02. Here's my original average observed time. 2 times 0.3 divided by 0.02 times 3.5, all squared, ends up being 73.5. So that means I need at least 74 observations, if that's my standard deviation, that's my original mean, to be 95.5% sure that I'm off by no more than 2%. So my initial 30 observations are not nearly enough. I need to go back and collect additional observations if I really want that much certainty in my estimate. And I think this is a good example because I read a lot of internship reports where the intern watches the worker do the time study for about 10 operations, or watches the worker do the job for about 10 iterations. And that's usually not nearly enough to get the reasonable estimate of the time required to do the job.